Welcome to rankstudent.com, the site preferred by millions of students around the world for digital education in science and technology. I'm Dr. Ahmed. I will be your host for this brief review of the very important chapter on the laws of motion. The topics covered in this chapter include Newton's first, second, and third law of motion, law of conservation of momentum, inertia, momentum, force, impulse, isolated systems, equilibrium, and free body diagram. It is said that physics, especially classical physics, is essentially Newton's law of motion, Newton's laws of motion. All else is footnotes. The laws of motion changed human civilization. If you were to look for bends in human history, the appearance of Sir Isaac Newton in the latter part of the 17th century marks a departure in the onward march of human progress. The Industrial Revolution, the steam engine, the automobile, airplanes, satellites and space travel, astrophysics, various kinds of wave motion, music, earthquakes, all of them can be explained through the laws of motion and owe their development to the work of Sir Isaac Newton. Newton's first law of motion is also called the law of inertia. It states that a body at rest continues to be at rest unless it is acted upon by an external force. A body in uniform motion continues to be in uniform motion unless it is acted upon by an external force. If the external force on a body is zero, it has no acceleration. Conversely, a body experiences acceleration only if it is acted upon by a net external force. A definition of momentum. Momentum is defined as the product of mass and velocity. P equals mv. It is a vector quantity and has the same direction as the velocity. Newton's very important second law of motion, the basis of classical physics if you would, states that the rate of change of momentum of a body is proportional to the net applied force. In other words, F equals a proportionality constant K times dP by dt, where P is the momentum. We can arbitrarily choose K to be 1, and therefore the law of motion can be stated as F equals ma, something that everyone knows or should know. The force is expressed in units of newtons. 1 newton is equal to 1 kilogram meter per second squared. Newton's second law of motion is a vector law. It can be resolved into its components in the x, y, and z directions. Fx equals max, Fy equals may, Fz equals maz, and in these equations only the net external forces are considered. Internal forces are disregarded. For instance, if there is a car at rest, and if you're seated inside of the car, you cannot push the car by yourself from the inside of the car. In order to move the car, someone outside the car has to push it. Newton's second law of motion is not affected by the previous history of motion of a body. The law is instantaneous at that point. As stated, the law has no memory. A definition of impulse. Impulse is the change in momentum. We know from Newton's second law of motion, F is equal to k times dp by dt, where p is the momentum and dp by dt is the rate of change of momentum. Therefore, impulse, which is the change in momentum, becomes equal to f dt, which is equal to force times duration of the time when the force is applied. Newton's third law of motion states that to every action there is an equal and opposite reaction. If you push on a wall with your thumb, the wall pushes back on your thumb with an equal and opposite force. In general, when two bodies A and B interact, the force on body A due to B is equal and opposite to the force of body B on A, stated in the form of an equation: FAB equals minus FBA. The law of conservation of momentum states that the total momentum of a collection of isolated objects is conserved. What is a collection of isolated objects? It is a collection of isolated objects on which there is no net external force. Very often, we consider our universe to be an isolated system. Whether or not it is, that's a different debate. But these kind of assumptions are made so that we can make some sense of the physical world. If two bodies A and B with momentums PA and PB interact, then PA plus PB equals PA prime plus PB prime, where PA prime and PB prime are momentums of A and B after the interaction. Equilibriums of bodies. This is an important concept. For a body to be in equilibrium, the vector sum of all the external forces acting on the body must be 0. F1 through Fn added up should be equal to 0. This is a vector equation, and it can be resolved along the three axes, 1 and 2 and 3. F1x plus F2x, etc., all the way up to Fnx equals 0. Similarly, along the second and the third axis. The forces that we most commonly experience in classical physics are: number 1, gravitational force is acting towards the center of the earth and is represented as minus g. The contact force, normal to a surface of contact, usually represented by capital N. Two bodies in contact have equal and opposite normal forces N and minus N. Static frictional forces equal to mu sub s times N, where mu sub s is the static coefficient of friction for a body at rest. When a body starts to move, dynamic frictional forces take over. The dynamic frictional force equals mu sub d times N, where mu sub d is the dynamic coefficient of friction for a body in motion. In general, mu sub d is less than mu sub s, but it could be very different too in different situations. Then we have the spring force or tension. That's equal to minus kx, where k is the spring constant, x is the displacement. In general, any elastic body will have a spring constant. Ways of reducing friction. We are familiar with these: lubrication, ball bearings, flotation on air, magnetic levitation, and so on. For instance, flotation and air. When we want to, in the laboratory, create a situation of zero gravity, sometimes we can create a test chamber wherein the object to be tested is floated on air. Magnetic levitation is used in high-speed trains, for instance, and in bearings wherein friction is very close to zero. Now, friction can be useful as well as hurtful. Sometimes it's useful because without friction we would not be able to, for instance, stop a car. Let's look at motion in a circle. A body moving in a circle, such as a stone attached to a rotating string, is subject to a centripetal force towards the center of rotation equal to F sub c equals mv squared over r. To counteract this force, there is an equal and opposite force on the stone of the same magnitude that shows up as tension in the spring. This is the centrifugal force. F sub t equals minus mv squared over r. This centrifugal force and the centripetal force are equal and opposite. Example, a car or a bike moving on a road on a circular path experiences a friction F that opposes its centrifugal tendency. It is subject to both centrifugal and centripetal forces and the friction F. Illustrated in this diagram are the various forces acting on a car moving around a circle on an incline. The resolution of the forces in the x and the y directions are given in these diagrams. I would recommend that you go over them and familiarize yourself as to how a body in equilibrium remains in equilibrium. A body in motion is subject to a force F. When we go through the resolution, we can see that the n cosine theta, which is shown by the vector pointing upwards, is equal to mg plus f sine theta. Mg is due to the gravity, F is due to the friction. Mg plus f sine theta. F is in this direction, sine theta is this way, mg is the gravitational force. Similarly, along the x-axis, we can show that n sine theta plus f cosine theta equals mv squared by r. You can see it here. The acceleration towards the center is v squared by r, therefore the force is mv squared over r, and the force is n sine theta plus f cosine theta oppose the mv squared by r. These two equations help us solve for the maximum possible velocity Vmax for a car moving on a curved road banked at an angle theta, or a flat road with no bank where theta is equal to 0, by substituting F equals mu sub kn when the frictional force is just sufficient to overcome the tendency to slip. This kind of resolution of forces and an examination of a body at rest or a body in motion is fundamental to understanding the mechanics of bodies either at rest or that are moving. Free body diagram is a very important concept in mechanics. Drawing a free body diagram for a body is one of the most powerful methods of setting up a problem in physics. How do we do that? Number one, include all external forces on the body. All external forces on the body. For a subsystem, that is a portion of the body that is extracted from a larger body, include all the forces from the other subsystems, but note that there is always an equal and opposite reaction on the other subsystems. As an illustration, I ask you to draw a free body diagram for a space station. Let's assume that it's moving in low Earth orbit around the Earth at a radius r with a velocity v. Assume that the propulsion force is exactly equal to the very small frictional force due to drag. This should be a fun problem for you to tackle. It is very important, and I would highly recommend that you practice with actual examples from previous tests, whether it be NEET, JEE, JEE Advanced, board exams, or other university entrance exams. One way to do that would be to log on to www.rankstudent.com, download onto your mobile phone, and practice often. Rankstudent.com provides you with over 100,000 questions, answers, answer elaborations. Practice helps solidify the concepts. I thank you for your attention and good luck with your practical examinations.